Hello and welcome to the YouTube channel D Creations Resources. Here we discuss several things related to science, and today we are going to talk about the Nobel Prize in Physics declared for the year 2025. In our previous episode, we have spoken about Nobel Prize in Medicine declared in 2025, and on 7th October, the Royal Swedish Academy of Sciences awarded the Nobel Prize in Physics to three scientists whose work has brought quantum phenomena, which was once thought to be limited to the microscopic world, into the more tangible macroscopic world. Clarke, Devoret, and Martinez are the three scientists who have won the Nobel Prize in Physics for the year 2025. Out of them, John Clarke was born in 1942 in Cambridge, UK. He got his PhD in 1968 from University of Cambridge, and currently he is a professor at University of California, Berkeley in USA. While Michael Devoret was born in 1953 in Paris, and he did his PhD in 1982 from Paris University of France. And currently he is professor at Yale University, New Haven, and University of California, Santa Barbara in USA. While the third Nobel laureate, John Martinez, was born in 1958, he did his PhD in 1987 from University of California, Berkeley, USA, and currently he is a professor at University of California, Santa Barbara, USA. These three have won the Nobel Prize for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. So we are going to understand this in simple terms. For that purpose, let us speak about these phenomena. So let's first talk about quantum tunneling. Now imagine that there is a big wall and you are playing with a ball which is rolling towards the big wall. Suppose you throw the ball towards the wall. Now the wall is going to be an obstacle. So the ball will have to stop. It can't go through the wall, right? Now this is the macroscopic world we know. Now when we come to quantum mechanics, things are different. In the tiny world of quantum physics, very small particles like, for example, electrons can sometimes magically go right through the wall as if it wasn't there. So this is called as tunneling, or specifically quantum tunneling. So it is as if instead of jumping over the wall, a tunnel has been dug inside the wall and the particle has passed through and popped out on the other side. That's why the name quantum tunneling. Now, to speak in the language of physics, here the particle passes through an energy barrier that it shouldn't be able to cross. Now, in physics, macroscopic objects like a real ball are known to follow rules of classical mechanics, while tiny objects like, for example, electrons are known to follow rules of quantum mechanics. And there are many interesting things. So these electrons, for example, can behave both like little balls and waves. They have a dual nature. And that is how this tunneling can be explained. So imagine as if there are two rooms. The particle is in the first room and it has kind of sneaked through and has entered the second room. So it has tunneled through. The next term was energy quantization. So energy quantization means energy comes in fixed little packets instead of any random amount you like. Imagine that you want to go somewhere and there are two ways. One is climbing stairs and other is walking up a ramp. Now a ramp lets you stop at any height, right? Or you can stand at any height when you are on a ramp. But that does not happen with stairs. Stairs will only let you stand on specific steps. So quantized energy is like stairs. You can be on one step or on the next step, but you can't be in between. So that's why we say that in quantum mechanics, these tiny particles like electrons can have only certain amounts of energy and nothing in between. In physics, this energy is given by the famous equation E is equal to h nu, where nu is the light's frequency and h is Planck's constant. So we spoke about two phenomena, namely quantum tunneling and energy quantization. Now earlier it was thought that such phenomena are confined only to quantum world. And people were aware that in quantum mechanics, several counterintuitive phenomena are considered. So particles are behaving like waves, or there's superposition, entanglement, tunneling, etc., etc. But one of the biggest challenges over the years has been bridging the gap between the quantum, that is tiny world, and the macroscopic, that is the large scale of world. So this year's Nobel laureates who won a Nobel Prize in Physics have addressed this challenge. Their work demonstrated the phenomena of quantum tunneling and discrete energy levels in electrical circuits which are large enough to be held in the hand. That's why in the beginning I said that due to work of these Nobel laureates, these quantum phenomena, which were once thought to be restricted to the microscopic world, have been brought into the more tangible macroscopic world. So it is as if the gap between the quantum and the macroscopic scales have been bridged. In 1984 and 1985, John Clarke, Michael Devoret and John Martinez conducted a series of experiments with an electronic circuit built of superconductors. Now you would want to know what superconductors are. So usually when current moves through wires, it faces some friction which we call as resistance. And this resistance makes things heat up and some energy could be wasted, etc., etc. But in a superconductor, when it becomes very cold, that means at very low temperatures, this resistance disappears completely. And current can flow forever without losing energy. Now, mind you, when I say low temperatures even less than the temperature of ice, okay, less than 0 degrees Celsius. And of course, this property is very useful because electricity can be carried super efficiently. It's not wasted due to the resistance. And it can also make magnets float above them, so which is called a Meissner effect, and you see them in some levitation based trains, or even in MRI machines at hospitals. Superconductors have been used, etc., etc. So in the work done by Nobel laureates, in the circuit, the superconducting components were separated by a thin layer of a non-conductive material. Now this situation where two superconductors are separated by a very thin barrier is called a Josephson junction. To give you an analogy, think of two rooms with a very thin invisible curtain between them. Now a normal ball can't pass through the curtain, but a magic whisper can be heard in the next room, right? So in a Josephson junction, this whisper is the supercurrent that can pass through without breaking the curtain. So this supercurrent can flow even if there is no voltage pushing it. So in simple words, a Josephson junction is a tiny quantum bridge where a special lossless current tunnels through a thin barrier. And this is useful, of course, for building ultra precise instruments, etc., etc. Now do note that Josephson junction is named after Brian Josephson, who had won a Nobel Prize in Physics in 1973. Now one of the Nobel laureates, John Clarke, was specialized in exploring a range of phenomena using superconductors and the Josephson junction. And by the mid-1980s, Michael Devoret joined John Clerke's research group. And together they worked on this microscopic quantum tunneling. So quantum tunneling no more limited to microscopic world, but also possible in macroscopic world. Now, as mentioned earlier, Clarke, Devoret and Martinez conducted experiments where they built an electrical circuit with two superconductors separated with a thin layer of non-conducting material. And in this experiment, they showed that they could control and investigate a phenomenon in which all the charged particles in the superconductor were behaving in unison. So this was as if all of them together are a single particle, and this is a particle-like system. So it is trapped in a state in which current flows without any voltage. In other words, this system, a macroscopic system, is showing its quantum character by using tunneling. And here the tunneling is used to escape the zero voltage state. Similarly, they could also show that this system is quantized. That means it absorbs or emits energy in specific amounts or packets. No wonder that the chair of the Nobel Committee for Physics, Ole Eriksson, while declaring today's award, said that it is wonderful to be able to celebrate the way that century-old quantum mechanics continually offers new surprises. And it's of course enormously useful, as quantum mechanics is the foundation of all digital technology. So now, when these Nobel laureates showed that these quantum effects can be seen in circuits that can be manipulated and studied in the lab, they have opened a gateway for controlling quantum behavior in devices which are large enough to engineer. So this is really critical for emerging technologies like quantum computers or quantum sensors or quantum cryptography, or this can be called as the next generation of quantum technology. So in simple terms, the Nobel Prize winning discovery is talking about macroscopic quantum tunneling and quantization of energy. That is, quantum effects which are normally seen only at the scale of atoms are actually observed in larger systems that can be seen with the naked eye. So in simple words, it means bigger things like tiny electric circuits can act in strange quantum ways. So the experiments by the Nobel laureates showed that these effects can happen in a device built from superconductors, and they showed that quantum rules can apply to more than just atoms and electrons. They can actually be applied to the circuits they had built. Now, seeing these quantum effects at larger scales is going to help scientists build new kinds of technologies, like mentioned earlier, like quantum computers, where quantum rules are used to process information much faster than normal computers. The communications can be more secure and ultra-sensitive measurements can be done in science, etc. So, this Nobel Prize winning experiments have shown that it's possible to design and control these quantum effects in devices which people can actually use. A new era for science and technology has been opened. So, this Nobel Prize winning discovery has brought quantum wonder from the invisible atoms to the tangible circuits which we can hold. And that is how it is heralding a new frontier in science and technology. So this work has helped to transform quantum mechanics from a blackboard theory into a real world full of applications. Thank you.